Well, good morning, everybody. I guess we should get started. Um, are there any immediate or urgent questions that we should explore before we jump back in with the sharks? Yeah. So one of the things I want to make sure we get into a little bit today is this question of Euler angles and starting the process of learning how to visualize 3D rotations, which I personally find very difficult. And I have observed that most people find it very difficult. For some reason, we're just not constructed um, in a way that lends itself to having good intuition about these things. So what I typically try to do in introducing these topics is to do sort of an arts and crafts day where we take our pipe cleaners and we make little coordinate axes that look sort of like this, and we practice visualizing rotations by manipulating these things. And I have personally always found this to be really helpful, and I would encourage you to get 3 sticks and label them X, Y, and Z and masking tape them together so that they form roughly a 3D standard basis. And I think that'll help a little bit. So where to begin here is this idea. Suppose we take something that looks like this. I guess, let me erase the board. That might help too. Okay, so here's our standard basis, right? And you can see we've got a green label on the Y, a red label on the X, a blue label on the Z, and the mnemonic is RGB corresponds to XYZ, XYZ. So that's helpful once you get used to it anyway, for keeping track of these things. All right. Okay, so here's the thing that we know is that you can take any orthogonal matrix. In other words, you imagine just putting the axes in any orientation you want, and you write down the coordinates of these axes according to the old coordinate system as the columns of a matrix, and that gives you a rotation matrix. Now, the thing that's not obvious, there are actually 2 things that are not obvious. Let's start with the first one, is that no matter what orientation you pick, you can get there only by composing rotations about the coordinate axes. And I think that's maybe the first thing to sort of define. This is due to Euler, which is why we call them Euler angles. You can make any 3D rotation by composing rotations. Well, I should say it like this, by composing 3 rotations about any choice of coordinate axes. All right. This is not at all obvious, and it's especially not obvious that this is even useful. No, it does turn out to be useful, and it's important to know this, because some of the time that you're working with rotations, you're going to want to think in terms of Euler angles. And the classic example of describing a rotation with Euler angles is, you see it if I put it on my head? Let me get the little one. Set up right, yes. No. Yeah. like this. All right, so I have my x-axis going that way and my y-axis going that way, and I'm looking in the negative z direction, right? And you often want to describe the orientation of a player or a vehicle or something like that in terms of what's called a head angle, which is which way am I facing? So this is a y rotation, combined with a pitch angle, which is am I looking this way or this way? And notice that's an x rotation, combined with a roll angle, which is am I turning my head from side to side, which you'll notice is a z rotation. And you typically combine these in a certain order, namely you would do it roll first, and then the pitch, and then the head. And because the way that you write them is backwards, this is called the head pitch roll connection, also known as yaw, pitch, and roll. So that's probably the most common use of Euler angles in practice, is describing an orientation in terms of head, pitch, and roll. And it sort of corresponds to the way that you might think of a first-person player. Of course, walking around with coordinate axes on his head might be directed to turn, right? So there's a roll, which is the side-to-side tilt, say, of the camera. Then there's a pitch angle, which would be around the x-axis done intrinsically, because I'm multiplying it on the left. And then the head angle. I'm sorry, I'm doing it extrinsically, because I'm multiplying on the left. And then the head angle, which is which way is it facing. So I guess that's a good example as a warm-up. But how do we sort of understand and exploit this idea that whatever orientation of the axes I pick, I can get there with 3 rotations about coordinate axes. So here's a good one to start with that is sort of an easy warm-up. I don't know how to make this as visible as possible, but we'll try it. Suppose I just do something like, instead of having x and y and z the way they normally are, what if I just sort of swap these around so that y is pointing towards you, z is to the right, and x is up. So that is a rotation of the coordinate axes. Can be described by a rotation matrix that's pretty easy to deduce. Because I'm still aligned with coordinate axes. What's happened is that, no, let's go on. So the question is, let's try to apply Euler's theorem and say, well, if this is true, then we should be able to get here from here by doing 3 rotations that are aligned with the original coordinate axes. And in fact, we will make it even better. In fact, I'm going to say you can do it with 2 rotations. And I can even say you can do it with 2 rotations that are positive 90 degrees. So let's draw this for the record. So we start out with something that looks like this. We have a z, we have an x, and we have a y sticking out. No. Wake up, Steve. We want to start out with y up there, and z is sticking out. So there's our standard basis in its usual orientation. And I'm asking us to picture a case where x is up and z is to the right. X is up. And y is the one that's sticking out. Okay, and that still works. It's still the same right-handed system. It's just been twisted around. And here's the challenge. We need to go from the left one to the right orientation using two 90-degree rotations about a coordinate axis. All right. So let's kind of do this together, since I don't have a good way to break us into small groups and discuss it side by side, I guess. So here we are, and here's where I want to end up. So one thing you might say is, okay, I could do a 90-degree rotation about z, and then a 90-degree rotation about the original y-axis, right? So z and then y. And notice when I'm doing my y, I'm doing it with respect to the original world frame, the original y-axis, which we call an extrinsic application. Although I'm beginning to debate whether that terminology is really helpful or not, but it probably is. So one way to do it is we'll do a z rotation followed by a y rotation. And by this, I mean, we're going to compose rotate y 90 times rotate z 90. You buy that? Right, that I do a z rotation and then a y rotation. It's sometimes easier to think of doing these intrinsically. So in other words, I would call this a z rotation and then intrinsically apply an x rotation, because that's where the reason this is easier is because I can see where the x-axis is now. If I want to do the y rotation, I have to imagine where the y-axis was. So that would be another way to describe the same thing, is a z rotation and then multiply on the right by an x rotation. And that's exactly the same transformation. So we might as well write them down together. So you could say, I have a z and then an x on the right. And that should be rotate z 90, rotate x 90. Right, so that's interesting. We're trying to get to this one. I guess that's why I put the picture up. Can you find some more? I guess that would be the next question. Again, restricting our attention to two axes, positive 90-degree rotations. How many different ways can we figure out to get there? How about if we do a y rotation first, and then intrinsically a z rotation? Right? That should certainly work. Right? So y rotation, and then this would be an x rotation on the left, or a z rotation on the right. Now the y rotation followed by the y rotation followed by the z rotation on the right, we've actually already described it here. But we could take that same sequence and think of it extrinsically. In other words, this is a oh no, that's the one we already have. Y. Just a second. I lost track of what I was doing. You do a z rotation and a y rotation. Yeah, that's the one we already did. I was losing my mind, I guess. No, what do we want to look at? there should be several other ways to do this. And oh, that's what I was doing. So the y rotation. Okay, so this is a z rotation first. Y rotation on the left. That's this. The other thing we could do is to say I have a y rotation and then a z rotation on the right. I could also say this is a y rotation, excuse me, a y rotation and an x rotation on the left would be another way to describe that. Is that right? Y rotation followed by, here's my world x-axis is right here. So we do a 90-degree x rotation extrinsically, so on the left, right? So, excuse me, y, x. So that's actually another one, right? We do y, and then x on the left would be another way to do it. And I think there are more, if I remember this correctly. So that one we just did. So the y rotation and then the x on the left can also be described as a y rotation and a z on the right. In other words, y and then, excuse me, y and then intrinsically z would be another way to do it. And let's see. So we've got it starting with y, starting with z, and starting with x. And I think that might be all of them, right? So I've got y. If I do y first, what are my choices? I can either follow y by an intrinsic z rotation or y with an extrinsic x rotation. So that gives me these two. If I start with x, ooh, this is new. Okay, I missed this one. Okay, if we start with x, do a 90-degree x rotation, then I can multiply on the right with a y rotation, so I get intrinsically a y rotation, and that will bring us back there. And that's this one, but I can also describe that right over here. We start with a 90-degree x rotation, and then extrinsically do a z rotation, and that puts us here. And that's this one, x followed by z. So you can think of it in 6 different ways, although in practice there are actually only three different combinations, because depending on whether you're thinking of the second rotation as being an intrinsic one or an extrinsic one, but it works out to be the same. So that's kind of an interesting observation, that we can get there through several different paths just by composing a sequence of rotations about the coordinate axes. Comments so far? Yeah, so let's do something that's more interesting and maybe a little harder to picture. And that would be, suppose I take standard orientation of the axes. Oh, yeah, that's a good question. So here's our axes. So a head would be a y rotation, and that corresponds to how you would turn your head. A pitch would be an x rotation, which corresponds to how you look up or look down. And then the roll would be a z rotation. So this terminology, well, head pitch roll or yaw pitch roll is, it comes from aviation, because you imagine this to be attitude of an airplane. As it's moving through the sky, it can roll. It has a pitch angle as it headed up or down, and it has a yaw, meaning is it oriented side to side as it moves through the sky. But I think I like to think of it as a head angle, not a yaw angle, because the word yaw doesn't mean anything to me. Yeah, cool. Let's do another one of these thought experiments with something that's a little bit, I say a little bit, something that is massively harder to picture. So if you start here and you let's do a negative 45-degree Y rotation. So like this. Okay, so like this. And then follow that by an X rotation of negative 45 degrees extrinsically. So I'm just going to take this thing and turn it. Here's my original x-axis. Turn it up like this. And this is chosen only because if we put a camera over here, it's fairly easy to visualize. All right, so let's go through that once again. Do I want to do, no, I take that back. Yeah, do a 45-degree Y rotation and then multiply on the right. So intrinsically a minus 45 X rotation. All right, so this is not unreasonable to picture. Notice that in the process of doing the Y rotation, the x-axis and also the z-axis are staying in the xz plane. Yeah, the xz plane. And then when I do an intrinsic X rotation, so I'm multiplying on the right by minus 45-degree X rotation, so clockwise, my x-axis is still in the xz plane. So try to hold that thought as you process the rest. And then these two guys are sticking up at 45-degree angles. Now the question is, according to Euler's theorem, we should be able to get there by doing 3 rotations about any set of coordinate axes. Now, obviously, it's easy to do it with the ones we just did, right? Right? It's easy to say, okay, we can get to here using minus 45-degree Y rotation and here with a minus 45-degree X rotation. Well and good. I think the exercise is actually easier to do if we think about what sequence of operations will undo this. And so clearly we can undo it just by inverting what we did. In other words, a positive 45-degree X rotation and a positive 45-degree Y rotation. Right, so positive is counterclockwise, so counterclockwise, counterclockwise. So, but that's the easy answer. The best way to think about extrinsic and intrinsic is, are you multiplying on the right or on the left of whatever existing transformation is happening? So if you haven't done anything yet, and I say, let's say a minus 45-degree X rotation, it's completely unambiguous because there is only one frame in the picture, namely the world frame. So minus 45 means minus 45. After I have done a minus 45 Y rotation, and then I say, apply a minus 45 X rotation, that has 2 possible interpretations, right? Do I mean rotate about the X-axis where it is now? In other words, relative to the transformed frame represented by the object as it is. And that would be I'm multiplying on the right because it's relative to the frame that's on the left. Or I could say, do it extrinsically, meaning let's think back to the world frame and remember where the X-axis was and rotate with respect to that. And the result is different. But in practice, in practice, the difference is if I'm taking my Y rotation let's write it down. I think this is a potentially confusing point and worth the effort. So if we take and apply rotate y minus 45, so going clockwise about the y-axis, there are two ways we could apply an x rotation. We can multiply on the left, or we could multiply on the right. And the distinction is that this is going to do the x rotation about the transformed x-axis. And this one is going to do the x rotation about the world x-axis. That's the distinction. And you know, the best way to get comfortable with this, I think, is to go back to that example. I think it's called Transformations 2, where we're working in 2 dimensions and you have some keys that can move the little triangle around. And you know, you can say, oh, well, okay, I'm going to apply a new transformation. I want it to be extrinsic or I want it to be intrinsic. And you can see the difference in action a little bit more easily there than you can trying to imagine what's happening in 3D space. But the way you should sort of picture this is that, remember, there's a left of rule that when we go to interpret, what does this mean? This is the world frame, and it says I'm applying this rotation with respect to the world frame, regardless of what else has happened to the model in the meantime. Whereas I'm applying this rotation with respect to a frame that has already been transformed. And I find that when I'm trying to understand how to do a transformation, thinking in terms of doing things intrinsically is often a lot simpler. In other words, when I have done a 45-degree or minus 45-degree y rotation, and I want to think about what to do next, it's easier for my mind anyway to picture where the x-axis is now and say I'm going to transform with respect to that axis, rather than trying to think about where the x-axis used to be. So that's possibly just me. I'm not sure. So anyway, here we are. So that's a good question. In both cases, do you apply the y rotation first? The answer is no. That would be, you would get different things happening. The y rotation is first here, because remember, these are just matrices. Matrix multiplication don't lie, right? This is going to happen first because when I put a coordinate vector in front of this matrix, it will be first multiplied by y and then by x, regardless of whether you group these by pre-multiplying the matrices. Over here, notice that if I put a coordinate vector on the right and I apply this, the x rotation is happening first. So these are different, right? It's just in our minds, we can think of it either way. But when you go to write down the matrices, it doesn't lie. You can see here, I'm applying a y rotation and then the x rotation. Here, the effect of thinking intrinsically is actually that the x rotation happens first. So if you just follow what it says here, this says do a y rotation and then do an x rotation, and we get this. Here it says do an x rotation and now do a y rotation, and we get this. It's just in getting to this, I find it easier to think of it as doing a y rotation and then multiplying on the right by an x rotation. Whereas if I think of it as doing the x rotation and then multiplying on the left by the y rotation, I have to, again, imagine in my mind where the old y-axis was, because that's what this is doing. So it's this notion of intrinsic versus extrinsic. It's kind of a point of view. The absolute reality is look at the matrices and the order they're multiplied, because that is exactly what is happening. Okay, I know. I feel your pain. I've spent a lot of hours holding things like this in my hands and weeping because I couldn't figure out what was going on. So let's think about this, and again, part of this is just to stretch our brains a little bit and make our heads hurt to some extent. So suppose I am in this new orientation, right, where I have done these two 45-degree clockwise rotations, and I get this thing that it's not too hard to visualize. Just remember, the x-axis is still sitting in the xz plane, because we haven't left the xz plane, and these guys are sticking up out of the plane at a 45-degree angle. And as I said, our goal is let's try to come up with a sequence of transformations about coordinate axes that will get us back to the standard orientation of our frame. And I think the one to start with is let's do YZY. Yes, and again, this is just a consequence of the fact that we're doing this with matrix multiplication. That you can't change the order without changing the meaning, and you can see that when I multiply a coordinate vector, this one happens first. It's the easiest way to think about it. Yeah. Let's do YZY. Maybe I should. So if we take the order YZY, what that means is you can take any rotation about the y-axis followed by any rotation about the z-axis and any rotation about the y-axis. And I chose this particular combination of three axes just because it's a relatively easy one to find, unlike some of the others that we may try later. So I'm here. This is my. I can never really figure out how to best show this on the camera, but it's something like this. So what are some of the options you might try? Well, what if we did a 90-degree y rotation? Now, what the effect of that is it gets the z-axis into the xz plane instead of the x-axis. That's basically all that's accomplishing. So we are here, we do a 90-degree y rotation here. And now you sort of think, well, okay, I'm allowed to now make a z rotation. So let's do this. We'll do a rotation about the z-axis. And now everything is good, right? I have the y-axis vertical, I have the z-axis in the xz plane, and I can do another y rotation to make the z-axis point forward as it should. So let's do that once or twice more. So where were we? We were originally here. Right? In other words, we did our clockwise 45-degree x rotation, clockwise 45-degree y rotation. And I'm claiming that if I do a 90-degree y rotation, again, I'm starting with that one, followed by a 45-degree z rotation, and then a minus 45-degree y rotation, that I should get back to where we were. So that seems, I hope, plausible. try it with your hands. To help guide us in this discussion, I got another idea, which is this is it's just a little experiment. Don't want it quite so big. And a little experiment I put together some years ago to try to, again, get my head around how these things work. And so we've got key controls that'll do like an incremental rotation about X or Y or Z. And so, for example, if I tell it to do, somebody said something. When we to answer your question, yeah, when we talk about extrinsic, word generally means I am doing it with respect to the world frame. And literally, in terms of code, it means I am multiplying on the left. So let's see. Yeah, so if I just press, say, the Y key, it'll do a 15-degree rotation counterclockwise about the Y-axis. So if I do this 6 times, I'm now aligned with the X-axis. 6 more times, I was 90 degrees, 90 degrees, and 90 degrees. Oops. And you can see the transformations accumulate. And you can sort of, for example, this is very easy to play with head, pitch, and roll. So if I do a, let's say let me clear this. If I do a Y rotation, that's my head angle. Then I do an X rotation, that's the pitch angle, and a Z rotation is the roll angle. And this is not very intuitive to do it in that order, because I'm doing this intrinsically, which is the backwards of what I really want, the way that we might think of it. So put this back. If we click on intrinsic and I do the same thing, when I can choose a head angle, and then when I do a pitch angle, it's going to multiply on the left. So it's rotating with respect to the current x-axis. And then when I do a roll, it's going to rotate with respect to the current z-axis. And that's kind of the natural way to think about a head, a pitch, and a roll. And if I can get the same effect doing it extrinsically if I just do it in the opposite order. In other words, I do the roll first, then the pitch, and then the head angle. Oops, why? So if we were going to do something like, say I want to do a 15-degree head angle, and let's say a 15-degree pitch angle, followed by a 90-degree roll, we could do this. We could do the same thing in the extrinsic sense just by reversing the order. So I would do my 90-degree Z rotation, followed by my 15-degree X rotation, followed by my 15-degree Y rotation, and we're in exactly the same spot. But notice how much easier it is to think about it in terms of doing the rotations with respect to the local frame, because it's kind of like I'm going to turn my head a certain direction, then I'm going to pitch up or down, and then I'm going to roll from side to side. And those things kind of make sense, because when I say roll, I am rotating around my own z-axis, right? Not around some other imaginary world z-axis. And so if you look at the order of operations there, y, x, z, notice that in reality, the z is happening first, right? The roll, then the x, the pitch, and then the y, the head. All right, so this is sort of useful for kind of developing some intuition about Euler angles in general. But in particular, I wanted to try out this theory that we should be able to, that's not really what it says. Let's look at the T key in a minute. So let's suppose we start out doing, say, the minus 45 degree y rotation, and then intrinsically the minus 45 degree x rotation. So this is the orientation of the axes that we were just playing with. And my claim was that we should be able to undo this by doing we'll have to think about this a little bit. A 90 degree y intrinsically. So we wanted a 90 degree y. Then intrinsic to that, we wanted a 45 degree z. And then intrinsic to that, a minus 45 degree y. That's what we were doing there. So let's try it. Okay, we should be able to do this. Although there's a 50-50 chance that I have gotten confused in setting this up. So let's see if we can do this. So I've got it checked intrinsic, meaning that when I press a key, it's going to multiply on the right, which is what I want it to do. I wanted this y to be with respect to the current location of the y-axis, in other words, the local frame. And so in this little clunky UI, I would press the Y key 6 times to get a 90 degree Y rotation, right? So let's try it. 1, 2, 3, 4, 5, 6. So notice it's rotating about the current Y axis. And it does appear that we've got the Z axis now lying in the XZ plane, in the horizontal plane. So then we would follow that with a 45 degree Z rotation. And again, this is 45 degrees is 3 times 15. So I press the Z key 3 times, 2, 3. And now it should be just a matter of doing a negative 45 degree Y rotation. And this is promising because notice I've got the Y axis aligned. So capital Y is that's a clockwise rotation. So 3 of those, and we're back where we started. So that's interesting, right? In other words, this is sort of a validation of Euler's claim that whatever rotation you have, you can get there by doing a sequence of 3 rotations about an arbitrary sequence of coordinate axes. And again, I chose YZY more or less arbitrarily, just knowing that as an exercise, it's a fairly easy one to visualize, easier than most, right? So that's, I don't know. Yeah, to answer the question on the floor there, sorry I missed it. This is not the same as inverting the rotations, right? Notice that this, well, yeah, just changing the order of the matrices doesn't invert the rotation. You have to change the order of the matrices and invert what the matrix does itself. So, so that's a good one, and I encourage you to try it. both in the software simulation and of course in real life. Now, what I'd like to do is let's do a harder one. Slightly harder, not impossibly harder. Let's try ZYZ. Again, in theory, I should be able to I know you can't actually see the whiteboard, but all I did is I wrote ZYZ to remind me what we're doing. And again, this is an arbitrary choice, but it's one that I'm fairly confident I can find again if I stare at it for a while. Let's put it that way. So once again, we're starting with 45 degrees clockwise about y, 45 degrees clockwise about x, done with a right multiplication. So we're back in this orientation, remembering again that the sorry, stop sharing. Okay, we're back where we started. So once again, we've got the x-axis sitting in the xz plane, in the horizontal plane, and then the z-axis and the y-axis sticking up at 45-degree angles. And yeah, so 45-degree clockwise y rotation, 45-degree clockwise x rotation done on the right. So my assignment is to figure out a sequence of rotations. I get to do any rotation about the z-axis, any rotation about the y-axis, and then any rotation about the z-axis. And this one is just a lot less obvious. And I think what I want to do is I want to rotate just far enough to bring the y-axis back into the xy plane. And I do not know a really good way to force you to visualize what I'm saying, but there's some angle of rotation. So here's my possible z rotations, right? So the z-axis is staying put, and I can rotate this way or this way, and there is some angle that will get the y-axis into the xy plane, and that's the one I want, and I think that'll become clear in a sec. So now the x-axis is sticking down below the horizontal plane, but I've got the y-axis in the xy plane, the vertical plane of the whiteboard. Okay, then what we can do, I think, we're allowed now to do a y rotation. And the thing I can do is, if I do a rotation of, again, some number of degrees, it's not necessarily obvious how much, I should be able to get the z-axis back where it belongs. In other words, back into the x z plane. So notice that in doing that rotation, I haven't moved the y-axis. The y-axis is still in the xy plane, and now I've got the z-axis in the xz plane, and I should be able to do one more rotation about z just to make the y-axis vertical, and then all should be good. All right, that is confusing, but let's see if we can do it. So this is going to be a z rotation clockwise for some small number of degrees, right? To get the y-axis into the xy plane. Then I want to do a y rotation counterclockwise some number of degrees to get the z-axis back into the xz plane. And then I can do a z rotation counterclockwise some number of degrees to get the y-axis vertical. And one of the things that I have done is sort of adapt an experiment in this example. Let me share screen again. Make sure I'm seeing the chat. Is once again, we can set this up easily enough to do our two clockwise rotations about x and y. The key controls that I have here do not necessarily lend themselves to experimenting with wacky angles. And what I wanted to just show you is if we go to the source for this example, I just added a sequence of key controls. So what this is going to do is here is our clockwise z rotation. Now, where the heck did I come up with minus 35 degrees? And the answer is several hours of trial and error. Again, just to try to work with this and get a sense for what was happening and confirm the intuition that I just had that we should be able to do that rotation. And again, the 60-degree Y rotation and then the 55-degree Z rotation these were obtained by trial and error. There are ways to get this analytically if you sort of get stuck. But I was more concerned with my 3D intuition than I was with doing the math with all the sines and cosines. So this is we should be able to make this happen if my estimates for these angles are at least approximately correct. I'm not claiming they're exact because I don't believe they are. But yeah, so if we go, so what do we have? We have there is our sort of our standard configuration, and I claim I can undo it by doing those 3 rotations. So first, in intrinsic mode, the P key should do this clockwise Z rotation that moves the y-axis into alignment with the xy plane. Then the Q key should do that 60-degree Z rotation, right? So 60-degree Z rotation should align, what's it supposed to do? Is that right? Oh no, we're doing ZYZ. Sorry. We did YZY in the previous example. Okay, scratch this. I just lost track of what we're doing. So, so we're doing ZYZ. So I'm claiming that I can do, there's our first Z rotation. The second one should be a 60-degree Y rotation that brings the Z axis down into the XY plane. And this is the nice thing, is that bringing the Z axis down into the XY plane, while the Y axis is in the XY plane, I mean, the Z axis down into the XZ plane, the horizontal one, it aligns it with the original world Z axis. And now we can do this now we can do a Z rotation to get the vertical axis aligned, which is our R key. And you can see from this little schmutz here that I don't have the angles 100% correct, but they're very close. Let's do it again because that was fun and the explanation was plenty garbled. So we do our counterclockwise Y of 45 degrees and our counterclockwise X of 45 degrees. So there we are. And I'm claiming that that we can do, and let's review what we're having here again. We can apply a minus 35 degree Z rotation. Let's try that. That's our P. Right, so that was a rotation about this. This is the z-axis. Counterclockwise, clockwise, so to the right, 35 degrees. The next one was a 60-degree y rotation. And then the next one was a 55-degree z rotation, which will reorient. You can see the y-axis here. It's sitting in that xy plane, and it just needs to be righted. And so that brings us upright. So one of the things I want to do on the homework that'll be coming up soon is to make you think through a couple more of these. And you're going to tear your hair out, I know it, because I'm speaking from personal experience. But I think it's really, really valuable as a thought experiment to try to visualize what's happening and come up with ways, again, to figure out how to do these manipulations. This is just for shits and giggles. I will show you this one thing, not that. This is actually a pretty nice article about Euler angles in general from Wikipedia, and you might take a look at it again and just try to think through what they're talking about and visualize it. This is where I picked up the terminology intrinsic versus extrinsic, by the way, which I have found useful in my own thinking. So there's this whole discussion about Euler angles, discussion of intrinsic versus extrinsic, many different possible conventions. Here they talk about head, pitch, roll, using slightly different terminology. But that's kind of, I've never noticed this before, this is new. That pitching is like a pitcher? I don't think so. But I'm scrolling through this because there's one thing I'm looking at, which is basically this tells you what the angles are going to be, in the sense that if you produce a rotation matrix, and basically the matrix describing a given rotation is unique, right? Because the matrix is determined by where are the axes, right? The columns of the matrix, the numbers making up those columns, are the coordinates of the newly located axes. The thing is, when you want to interpret that in terms of Euler angles, there's many possible interpretations. So you could take our, where were we? Let's say our YZY, and you could look at the numbers in the matrix. From those numbers, you can say, okay, well, the number in the center is the cosine of the second angle. And using that, you can determine the second angle. The first number in that column is the negative of the cosine of the first angle times the sine of the second angle. But you already know the second angle, so you can solve for the first angle. And so if you're willing to do a bunch of this kind of ridiculous work, you can analytically determine what the rotation angles are for any combination of three axes. And when the three axes are all different, they call these Tate-Bryan angles rather than Euler angles, but I don't think anybody else besides the Wikipedia page uses that terminology. These are always called Euler angles, sloppily, right? But strictly speaking, what Euler was doing was he would have rotations, three rotations about two coordinate axes, rather than three rotations about possibly three different coordinate axes, as you see in the right-hand column. So this is not necessarily a fun thing to do, and that's why I'm not suggesting it. I think a fun thing to do is to try to hold a pair of coordinate axes, set of coordinate axes in your hands, and visualize what rotations are needed try to guess the angles. And one of the things that can be helpful is, for example, I'm claiming that the purpose of that first rotation was to bring the y-axis back into the xy plane. And one of the things you can do when you're playing with this stuff is we can easily change the camera position just by changing the view matrix. So here you notice that I have the camera positioned up in the what you might call the first octant, right? So we're getting this oblique view. What if I aligned the camera? What if I put the camera right in the XY plane somewhere? And it might be easier to picture what's happening or what is supposed to happen in that, let's see. So if I just go put my eye position just out the x-axis and look at the origin. Let's try that. All right, so now the positive x-axis is pointing at my eyeball, right? So it's basically invisible. And now let's try the same experiment again. Let's go back to intrinsic. We'll do y negative 45, and then do x negative 45. And now the claim is that by doing that minus 35 degree z rotation, I'm going to bring the y-axis back into the xy plane. So in effect, the y-axis should become essentially invisible if I do this right. And so that's the P key. And that's essentially the experiment that tells me what that angle should be, right? So if we, I guess I can't undo that. I have to start over. Yeah, so we do y, 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 x, x, x. And then I start doing negative z rotations. In other words, rather than putting in minus 35, I'll do minus 15 and then minus 30. I can see, well, if I just go a little bit more, I would get the z-axis aligned in that plane. And I'm telling you that because this is kind of how I started my trial and error process to figure out, well, can I deduce what those angles should be by playing around with this? Anyway, I don't know. Let's pause for questions or comments, I guess. Okay, so we will see eventually that, again, when you're talking about orientation of say, a first person in a game or something like an airplane or a vehicle, that this notion of head and pitch and roll can be a useful way to think about things. One thing I think to add on here, relative to this notion of head, pitch, and roll, I think this is a good time to introduce what are called spherical coordinates, because if you ignore the roll for a second, then just looking at the head and pitch angles gives you a nice way to describe an orientation of, say, a vertical axis, and therefore to describe locations of points. And this is a good thing to have in our toolkit. Well, let me stop sharing the screen, and I will go back to the real world here. So let me see if I can make sense out of this. So if you take your x and your y and your z, now imagine that you this is really hard for me to do. So you do I'm going the wrong way. Yeah. So this is our head angle. And so imagine you've done a rotation that way, and then you have a pitch angle, which is the X rotation. And probably drawn this in a way that is going to make it impossible to picture. I may have to resort to a canned illustration to get this to come out right. So what I'm trying to do is I'm trying to imagine the y-axis pointing up at some other angle. And the way that angle is described, I have done some amount of rotation this direction, and I have done some amount of rotation this direction. This is our head angle, and this is our pitch angle. And notice that by a combination of these two angles, you can orient this vector anywhere you want. And this would be a right angle there. You can kind of picture what I'm trying to get at. Now, if I also give you a distance from the origin, which we could call r, notice that that specifies a point in space. If you've had Calc 3, you will have encountered spherical coordinates. And that's what this is, that instead of specifying x, y, and z, you can specify a point in space using a head angle, a pitch angle, and a radial distance from the origin. And these angles are typically known as phi and theta. And the radial distance is often called by the Greek letter rho when you see this in math books or physics books. Yes, flashbacks to Calc 3 is right. Yeah, I think spherical coordinates is completely analogous to the polar coordinate system in 2 dimensions. But in polar coordinates in 2 dimensions, you have one angle and one radial distance, and here we have 2 angles and a radial distance. So one of the things that makes this useful is that this becomes an easy way to define a rotation matrix about an arbitrary axis. Because if you think of your axis of rotation as being the y-axis, and then you apply a pitch angle and a head angle, you can orient that y-axis wherever you want, and then just perform a y rotation, and that'll give you a rotation around that new axis. I'll show you a little experiment that I think is useful for this, which is here. Well, let me show you you're going to have the same problem we had before, no doubt. Workspace, transformations. Which one is it? Rotating cube axis test. Okay, now I know that the animation may be tough to see, but you can see what it's doing is I'm rotating. Notice that this point of the cube, if you can see my cursor, is standing still. So I am literally performing a rotation, not about any of the coordinate axes, but around an axis aligned with the vector 1, 1, 1. Right, so just pointing directly into the center of the first octave there. And I think it's interesting to ponder, well, what are some ways that we could do this? And let's look at the code. This is not the code. This is something else. So rotating cube axis test JS. So most of this is the same rotating cube code that we have seen before, or use a quaternion. What the heck is a quaternion? Get me out of here. This is the one I want to look at. So the first question is, how do we figure out the angles if the axis I want is the line through 1, 1, 1? Okay, so a little tiny amount of trigonometry tells us the head angle is 45 degrees, and the pitch angle is the arctangent of the square root of 2. If we have time in the next 3 minutes, I'll derive that for you, but it's not hard. So there's my pitch angle, and I'm going to do this. I'm defining a new matrix A, which is the pitch rotation followed by the head rotation. I'm also going to define the inverse of A, which is the opposite of the head rotation followed by the opposite of the pitch rotation. And then I'm going to make a Y rotation about an angle that increases 1 degree per frame. So there's my angle. And we'll multiply them together using that pattern of I do the inverse of A. So essentially, A is the transformation to a new frame in which the y-axis is at the angle that I want to do a rotation about. So I use that pattern of inverting A, doing the rotation about the world frame, and then redoing the A operation. So that's what's going on here. And then we just make that our model matrix. And that's it. And you can see it actually does work. This trick of undoing a pitch and head rotation to get back to the origin, and then performing the rotation about the world y-axis and redoing the pitch and head to put the cube back where it was. And that matrix will have this effect. So this is one way that we can sort of derive a general strategy to do rotations about any axis, not just the x rotations, the y rotations, and the z rotations that we started out with in 3 dimensions. We're about out of time, so I won't go into the rest of that example where I show you 2 different ways of doing that. But we'll come back to that next time, I suppose. Questions or comments about any of this before we part for the next 2 days? All righty then. I guess I may see some of you on Piazza tonight. If I don't see you first. Oh, the shirt, like all of my geeky shirts, came from my older daughter, who is officially the geek in the family. She's a web developer. She works for LinkedIn. I have a lot more. She just sent me 3 more for a recent birthday. Once I get them through the laundry, I'll have to show you. Anyway, all right. I'll try to remember to do that, see if she wants to tell me. Everybody have a great couple of days until Thursday. I'll see you then. All right. I'll hang around for a sec to see if there are urgent questions on the homework. See you later.